Welcome back, physics fans. We are deep into accelerations, and today we're going to add to our arsenal of equations to help us with motion problems. We'll be looking at kinematics, the big six equations of kinematics, and applying the big six. Well, remember from an earlier lesson that kinematics is the study of motion. The first quantity we defined with kinematics was velocity, a vector displacement per unit time. And the same equation is used for speed and velocity. V is d over t. We then changed our velocities and put in an acceleration, also a vector. It is the rate at which velocity changes. A is delta v over t, or in its working form, A is v minus v naught over t. Well, look at what we can solve for. Where am I when? How fast am I traveling? And how fast am I getting faster? All with our first two equations. Well, now what? Those can be the only two possible equations we need for kinematics. There can't be anything else, can there? No, another there is. Oh, that's right. What if we put acceleration and velocity equations together? With a little help from the dreaded acceleration algebra, we get the big six equations of kinematics. Dun, dun, dun. Well, let's see. Our first equation of kinematics. We already have it. It is the acceleration definition equation, or A is v minus v naught over t. Our second equation for kinematics, you will recognize this as an algebraic manipulation of the acceleration equation. It's one we use quite often. If we start with A is v minus v naught over t and do a little algebra, I can solve for final velocity, v. If I'm given the initial velocity, the acceleration, and the time. For this, I have the final velocity equation. V is v naught plus at. Likewise, I can solve for distance using Galileo's law of falling bodies. I can find the displacement an object travels during acceleration if I know its initial velocity, its acceleration, and its time. This is the displacement equation with initial velocity. D is v naught t plus 1/2 at squared. But since v is v naught plus at, with a little algebra, I can find the displacement if I know the final velocity, the acceleration, and the time. This gives me the displacement equation with final velocity. D is vt minus 1/2 at squared. And as we're going to see, parentheses are important. We have our fifth kinematics equation. Now this one is seldom used. It works only in one specific situation, and I prefer to use the others whenever possible. This is another displacement equation. It will let me find displacement if I know the initial velocity, the final velocity, and the time. This equation is the displacement equation with average velocity. D is 1/2 v plus v naught t, where by definition v plus v naught divided by 2 is the average velocity. And then finally, one of the more powerful of the big six will let me find my final velocity if I know the initial velocity, the acceleration, and the displacement. Notice, this is the only one of the big six that does not have time involved. Well, this is called the v squared equation, because it lets me solve for the final velocity squared. V squared is V naught squared plus 2AD. Or if I'm only interested in the final velocity and I'm not interested in any of the other parts, then I can solve for V by remembering to take the square root of the entire quantity, V naught squared plus 2AD. And as you will see with this one, parentheses are especially important. So the big six equations, the acceleration equation, the final velocity equation, the initial velocity displacement equation, the final velocity displacement equation, the V squared equation, and the average velocity equation. Each of these will let me solve for all of the displacement characteristics. And if I were you, I would put a box around these three, or highlight them, or underline them, or put stars by them, because you will be using these three in their original forms again and again and again. Now, there is something you have to remember with these. A big warning. These all assume we will be ignoring air resistance. Now, in the real world, we can't ignore air resistance. There is a force called drag, which robs some of the energy of everything moving through it. But this is Coach Roop's ideal classroom. The ideal classroom? Well, yes, that means in Coach Roop's classroom, we ignore a bunch of stuff. We consider the ideal cases so we can ignore air resistance. But armed with kinematics, now look what we can solve for. You can find out where something is, when, how fast it was going in the past, how fast it will be going in the future, and how much that change is going to be. Kinematics lets you predict the future or the past without traveling to either one. So we were able today to define kinematics, identify the big six, and apply the big six. So this is why writing the givens is so important. You've gone from 2 equations to 8 in one lecture. The givens will tell you which equation to solve. So the givens, displacement, initial velocity, final velocity, time, and acceleration, tells you which equation to pick. Read it, diagram it, write the givens. What am I looking for? All the setup to pick the right equation. And remember, while now we're up to 8, by the end of the semester, we'll be looking at 60 equations to pick from. So we've hit the targets, let's apply them. You know me, whenever I have a physics problem, let's take it out for a test spin, see what happens. A car starts with an initial velocity of 15 meters per second and accelerates at 4.5 meters per second squared for 5 seconds. Determine the car's displacement. Well, I've read it. After I read it, the next thing I always do is correct, diagram it. Here's the car of science at 15 meters per second. It'll accelerate at 4.5 meters per second squared for 5 seconds. We want to know the displacement. Read it, diagrammed it. After I diagram it, the next thing you do is correct the givens. V naught is 15 meters per second. The acceleration is 4.5 meters per second squared for a time of 5 seconds. Read it, diagrammed it, written the givens. Now I have to identify what I'm looking for, the displacement. So I need to look at the big six and choose an equation that let me find displacement if I know initial velocity, acceleration, and time. Of the big six, one fits. That is the displacement equation with initial velocity from Galileo's law of falling bodies. D is V naught t plus 1/2 at squared. Well, read it, diagrammed, written, given, known, looking for, picked my equation. Do I have to do any algebra? No, and it's always a good day when I don't have to do algebra. Whoopee-tie-yo-ki-yay, plug and chug. And remember, parentheses are important. Everything you learned in sixth grade about order of operations applies to physics. Well, parentheses are important. Grab your calculator, go. How far did this car travel? Correctamundo, 131.25 meters. Let's look at our second. Physics students drive their car with an initial velocity of 15 meters per second in a school zone. Well, 15 meters per second is, of course, 35 miles an hour in a school zone, which is 25 miles per hour. Suddenly, dun, 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 dun. Spotting a police officer, the student accelerates at a negative 4.5 meters per second squared for 25 meters. Determine the car's final velocity. Well, read it, diagram it. And again, here comes the car of science racing through our problem. Read it, diagrammed it. After I diagram it, the next thing I do is the givens. V naught is 15 meters per second. A is a negative 4.5 meters per second squared. And remember, a negative acceleration means it's doing what? Correct, decelerating or slowing down. For a distance of 25 meters. Read it, diagrammed it, written the givens. Now I identify what I'm looking for, velocity. Final velocity is going back to the big six. Well, as I look at the givens, I don't have time listed anywhere, and there is only one big six equation that does not have time, the v squared equation. But I don't want to solve for v squared. I want v. So how do I get rid of that squared? Correct. With a little algebra, taking the square root. V is the square root of the quantity v naught squared plus 2 times a times d. Read it, diagram, written, givens, known for, pick my equation. Although both forms of this equation will appear on your cover sheet for your test. Finally, the last thing to do, plug and chug. Notice you have to open two sets of parentheses and close two sets of parentheses. So grab your calculators. V equals the square root of, open a parentheses, 15 squared plus, open a second parentheses, 2 times a negative 4.5, careful, not 2 minus 4.5, but 2 times a negative 4.5, times 25, close both parentheses. Plug and chug, what do you get? Correct, 0. The car stopped. Now careful, with some of the TI-30s or some of the Casios, and especially with some of the phone calculators, you need to do the entire interior before you take the square root. In that case, for your calculator, you would take 15 squared plus, open a parentheses, 2 times negative 4.5 times 25, close the parentheses, equals. That will give you a number. Take the square root of that number to get the answer, 0 meters per second. Let's look at still another. The massive wad of chewing gum falls from the rest of the top of the Empire State Building and reaches the ground 9.51 seconds later. How tall is the Empire State Building? Well, how rude. Someone with used chewing gum on the Empire State Building would lean into the fence and spit the gum off of the Empire State Building with a stopwatch to see how long it falls. And that's a long time to fall. The Empire State Building is part of a race that happened back in early America, or mid part of the 20th century, between two architects, one designing the Chrysler Building and the other the Empire State Building. Well, living space in the Empire State Building was going to be taller. The architect at the Chrysler Building was looking for more art in his design, so he applies the Art Deco cap to the top of the Chrysler Building. The gargoyles located at the corners, the brushed aluminum up to the top, and as he submitted his design, he had the tallest building in the world. And then the architect submits the design for the Empire State Building. And with the addition of this structure, which actually, as we will see, will serve a purpose, he has the tallest building in the world. Well, the Chrysler Building architect had a little trick up his sleeve, and so he waited. And the architect on the Empire State Building is nearing completion, so the architect for the Chrysler Building adds a radio antenna. Radio will be broadcast from the Chrysler Building, and this radio antenna will make the Chrysler Building the tallest building in the world. Ha ha, he wins. Oh, but the Empire State Building architect has a little trick up his sleeve. Hiding in the top floor of the Empire State Building is his own radio antenna, which, when it is completed, will make the Empire State Building the tallest building in the world. A race to see who's tallest. Oh, and remember I said this structure here serves a purpose? It did. It actually had some purpose for what was then called the world of the future. This is a dirigible landing mast, a mooring mast that was meant to hold dirigibles. You recognize this one. The idea was that you would leave Europe in your hydrogen gas-filled dirigible and sail above the Atlantic, land in New York City, right downtown, moor your dirigible to this mast, and they would pull you in. And then you would walk down a gangplank into the Empire State Building and be in downtown Manhattan, the center of the world, without ever having to land in New Jersey at their dirigible docking stations. Well, this, of course, had one design problem. The dirigible itself filled with very explosive hydrogen gas. And we all know what happens to the Hindenburg. It lands in New Jersey before the Empire State Building is finished, right after a thunderstorm had gone through the area. Everything has covered with free electrons looking for a place to go. And as the Hindenburg got close, literally a lightning bolt jumps from the mooring mast to the Hindenburg, and oh, the humanity! Well, let's go back to our problem. A massive wad of used chewing gum falls from rest at the top of the Empire State Building and reaches the ground 9.51 seconds later. Determine the height of the Empire State Building. Read it. After I read it, I always diagram it. Well, here's my wad of chewing gum falling for 9.51 seconds. Oh, by the way, no extra credit for your architecture, artwork, and being able to draw the Empire State Building. Read it, diagrammed it. Next thing I do is correct the givens. T is 9.51 seconds, and the initial velocity is 0. That's going to help. The acceleration is, wait a minute, it doesn't tell me the acceleration. It just tells me a time and an initial velocity, rest. Oh, but wait, it does tell me it's falling. So if it's falling, it means the acceleration is g, 9.8 meters per second squared, the acceleration of gravity. What is the displacement? Well, initial velocity, acceleration, time, and displacement. I only have one equation that fits these givens. The law of falling bodies, d is v naught t plus 1/2 at squared. Ooh, but remember, my initial velocity is 0. And 0 times anything is correct. This is going to go away. D then is 1/2 at squared, or 0.5 times 9.8 times 9.51 squared. Careful, 9.51 is the only number you square. You don't square the whole thing, you only square the time. Grab your calculators and correct. The Empire State Building is 443.16 meters tall. 4.5 football fields straight up. Let me tell you, it is something to stand there down at street level looking up at that building. Let's try one more. A massive wad of used chewing gum falls from the rest at the top of the Empire State Building and reaches the ground 9.51 seconds later. What is the velocity of the chewing gum as it reaches your worstest enemy's head? Oh, look, there's somebody from Spring Lake, a Spring Lake Laker. Well, that's rude. But how fast is it going as it reaches the ground? Well, read it, diagram it. The object reaches the ground 9.51 seconds later. Then list the givens, the time at 9.51 seconds. The acceleration is, again, g, because it is falling 9.8 meters per second squared. I know the height of the building is 443.16 meters. What is the velocity? Well, turns out there are two ways I can go with this equation. The first, what's final velocity? If I know my initial velocity, it's at rest, acceleration, and time. Well, I could use the final velocity equation. V is v naught plus at. V naught, of course, is still 0. It will go away. So the velocity is a times t, or 9.8 times 9.51. The velocity as it reaches the ground? Correct, 93.2 meters per second. But as I said, there's more than one way to get to the results of this problem. With those same givens, the initial velocity at rest and an acceleration in the distance, I could have gone with the v squared equation, solving for the square root. I'm left with v is the square root of v naught squared plus 2ad. Plug, chug. Again, the initial velocity is 0. That will go away. So I have the square root of 2 times 9.8 times 443.16 meters. Grab your calculators, plug and chug. Correct. The final velocity, 93.2 meters per second. It doesn't matter which of the equations I chose, the final velocity equation or the v squared equation, they both give me exactly the same answer. Hey, physics works! Yes! The big 6 equations of kinematics. Remember, these only apply in the absence of air resistance. But if we can ignore air resistance, then A is v minus v naught over t, the acceleration definition, or v is v naught plus at, the final velocity equation, or d is v naught t plus 1/2 at squared, the initial velocity displacement equation, or d is vt minus 1/2 at squared, the final velocity displacement equation. The v squared equation, v squared is v naught squared plus 2ad, or to solve for final velocity, v is the square root of v naught squared plus 2ad. And the average velocity equation, d is 1/2 v plus v naught t. The big six: where am I? When? How fast am I going now? How fast was I going before? And what is my final velocity or my displacement? A lot you can solve with for kinematics.